Okay, we are live. So hello everyone and welcome to session 203 of the Latin American webinars on physics. This is Joel Jones from the PUCP in Peru and I will be your host today. So we are having Andreas Crivellin as a speaker. Andreas carried out his PhD at KIT in Karlsruhe, Germany, which was followed by postdocs at Bern and CERN. He continued his career then as Ambizione Fellow at PSI and then held an SNF professorship at Zurich, all in Switzerland. He is now a research professor at ICREA and the Universidad Autónoma de Barcelona in Spain. Now today, Andreas will give us an update on the LHC hints of new scalar bosons with masses around 95 and 152 GeV and their role in differential top-quark distributions. We are very happy to have him as a speaker today. Before we begin, let me remind the viewers that you can ask questions and make comments via the YouTube live chat system as usual. However, the different feature of this webinar is that the questions will not be at the end, but will be passed on immediately to Andreas during the talk. We'll see how this goes regarding the time, but we think that this will work very nicely. So without anything else to say, let me pass the microphone to Andreas. Please go on.
Thank you very much for the invitation. I'm very happy to talk about new Higgs bosons at the LHC. And Joel, as you said, please ask questions at any time. Make it as interactive as possible. And I think then this will be great fun for everyone. Okay, so I hope you can see my screen.
Yes, perfect.
It's there? Perfect. Okay, perfect. So I want to answer the question, or at least give a hint to the answer. Is there only one Higgs boson? Here you already see the iconic picture of an event which is most likely the standard model Higgs, which was taken at CMS. So here, this is the collision point, and these two green bars, this is the energy deposit of two high energetic photons. And if you look at their invariant mass, this is in fact close to 125 GeV. So it's very likely that this is from the decay of a standard model Higgs boson. But as always in quantum mechanics, you don't know for sure. It's only about statistics. And only once you have acquired enough events, you can see, you can make a statistical test and say it's highly likely that there is a Higgs boson. But as I said, in quantum mechanics, you can never be sure about anything. One event alone can always be just a statistical fluctuation. Okay, so here's the outline of the talk. I want to review for you the standard model of particle physics. So this is for the non-experts. Also, I want to tell you about spontaneous symmetry breaking, the standard model Higgs sector, how in the standard model Higgses are produced and decays. Then I come to the problems of the Higgs sector and how this points towards new scalar bosons. And I want to talk about the indications for new Higgses, of course. So here is the standard model of particle physics. As you see, the fundamental constituents of matter are quarks and leptons. Everything around us is made out of quarks and leptons of the first generation. So up and down quarks make up protons and neutrons within nuclei. And the electrons are, of course, in the shell of atoms. They come together with the, in principle, massless neutrinos. And now you see we have three copies or three generations of fermions. They have identical properties, except that they have different masses. Now here you see the heavy version of the up quark is the charm, and the very heavy one is the top. Similarly, for down quarks, you have strange quarks and bottom quarks, and for leptons, you have electron, muon, and tau. In addition, you have the photon for the electromagnetic interactions, the gluon for the strong interactions, so only quarks carry color charge, so gluons only interact with quarks, and you have the weak gauge bosons, the C and the W, which acquire their masses from spontaneous symmetry breaking. I will come to this later. And here the Higgs boson is famously involved. Now, the Higgs is the only scalar particle in the Standard Model, or better to say, the only fundamental scalar particle in the Standard Model. And it gives masses to all fundamental fermions as well as to the C and the W boson. Now, there are some masses you should take into account now to understand the rest of the talk. So first of all, the mass of a proton is quite precisely 1 GeV. Now, the heaviest particle in the Standard Model is the top quark with around 174 GeV mass. And now, if you take the usual convention for the VEF of the Higgs, for the vacuum expectation value, this is also around 174 GeV. So the top quark, as you will see later, is the only fermion with order 1 coupling to the Higgs boson. And so it's also the fermion which is most important for Higgs physics. So for later, as I said, for Higgs bosons, the mass of the particle matters. So what is important for Higgs physics is the top with 174 GeV, the bottom quark with around 4 GeV, the C boson with 90 GeV, the W boson with 80 GeV, and of course the Higgs boson with 125 GeV. So this is very important to understand the later stuff of the talk, because, for example, you see the W mass is more than 1/2 of the Higgs boson mass. So the Higgs cannot decay directly to W boson. I will come to this later. So for Higgs physics, in principle, the light stuff all doesn't matter. The only thing that matters for Higgs physics is top, bottom, WC, and of course the Higgs boson itself, but also photons and gluons, as you will see later. So, how does the Higgs interact? Now here, I hope you all know quantum electrodynamics. Here's a Feynman diagram showing the interaction of a photon with an electron. So this is how you draw it: an incoming electron, an outgoing electron, and this couples to a photon proportional to the electric charge of the electron. For Higgs interactions, it's similar. So the Higgs interacts with the fermions, or also with gauge bosons, always proportional to their mass. Now, this proportionality factor for the top quarks here is the top Yukawa coupling. So top quark mass over VEF is top Yukawa coupling. So you see the interaction strength of the Higgs is its Yukawa coupling, or for gauge bosons, it turns out to be the electroweak gauge coupling with some normalization, which is around 0.6. But the top quark Yukawa is the only one which of all 1. But just the takeaway message here, the Higgs couples to fermions and gauge bosons proportional to their mass. The rest is in principle the same as in quantum electrodynamics. Now, the important ingredient to understand about Higgs physics is the concept of spontaneous symmetry breaking. So unfortunately, I'm not in the seminar room. I can't take a rod and show you how it bends. So you must use a little bit more imagination. So here, this is a rod, this black line. And you see, if you turn this rod, the system remains invariant under rotations. So this is an unbroken symmetry. Now, if you would have a force which is perpendicular to the rod, this explicitly breaks the symmetry, because you can't turn the system around anymore around the axis of the rod, because the force bends it. So this case, the symmetry is really completely lost, and this is explicit symmetry breaking. Now, spontaneous symmetry breaking is different in the sense that here you still have the symmetry before until you reach a critical value for the force. And this also translates then to field theory, where it means unless you go below a critical value of the energy. So here you can imagine the force is just parallel to your rod. And as long as it's parallel, the symmetry is still there. However, once the force gets too strong, the rod will bend in some direction, and then the symmetry is not there anymore. However, the symmetry is only hidden in the sense that you don't know in which direction the rod will bend. In fact, any direction is as likely. So this restores the symmetry in this case. So that this is the new ground state where the rod is bent, can happen in any direction. So this is why one says the symmetry is only hidden, but not explicitly broken. And now this is what's happening for the Higgs potential. So the Higgs potential is as simple as it could be. It's just this quartic potential. And now if this mu squared term gets negative, the minimum of your potential is not at zero field values anymore, but at the square root of minus mu squared over lambda squared. And this is in fact your vacuum expectation value. And then this brings you to the famous Mexican head potential. Now you see, if mu squared is negative, then the minimum is not at zero anymore, but here at V. But the symmetry is only hidden. If you can look on this Mexican head from outside, you see the Mexican head has still this rotational symmetry if you turn it around its center. However, if you are at the minimum at the vacuum, at your vacuum expectation value V here, then from this point, you cannot see the symmetry anymore. If you turned around the Mexican head, around this position, I hope you can see my cursor. So if you turned around the position here at the yellow ball, which is lying within the Mexican head potential, if you turned around the Mexican head here, it wouldn't look like a symmetry anymore. And now another important thing here is you can have excitations along this circle here. There you see that it's flat. And flat means there is no mass turn. This then will correspond to the Goldstone mode, which is the one which will give mass to the W and the C boson. But excitations perpendicular to the circle, you see that you have a quadratic potential, at least to a first approximation, and this corresponds to a mass term. And this is then the physical Higgs boson. So excitations perpendicular give you the physical Higgs, excitations along the circle give you the massless Goldstone boson. Now, as I said, from mu squared and lambda, you can calculate the vacuum expectation value, the value at which the potential has its minimum value. And then what you see here is you can replace your Higgs by the vacuum expectation value, and then this is how you get your mass. So Yukawa coupling times vacuum expectation value gives you your mass. So this shows you why in electroweak symmetry breaking, the mass is proportional to the Yukawa coupling. Okay, so this was the theory part of the introduction. Now let's come to the phenomenological part. How do we find Higgs bosons? So how did we find the one Higgs boson which was discovered in 2012? So what is done at CERN, so here is this beautiful 27-kilometer ring below Geneva, where we have the interaction points here at the two experiments, ATLAS and CMS. Here, what you do is you collide protons with very high energies. Now, at low energies, protons mainly consist of the valence quarks, meaning up and down quarks. However, at high energies, it's even more likely to find a gluon within a proton than an up or a down quark. So at very high energies, a proton collider is in principle a gluon collider. And then this is how you can produce your Higgs boson. So the Higgs only relevantly couples, as we said, to top W and C. Now W and C, they don't couple to gluons because they don't carry strong charge. So here the relevant thing is the top quark. This has a large Yukawa coupling and it couples to gluons. And then you can see here that this induces at the loop level a coupling of the Higgs boson to two gluons. And this is how you dominantly produce the standard model Higgs at a hadron collider. Now, in fact, what is interesting, the standard model Higgs is the only particle ever discovered which is only produced via such a loop effect, so meaning via quantum fluctuations. All other particles, like top, WC, all of them were produced directly. However, only the Higgs is the one which, if there were no quantum fluctuations, you couldn't even produce it at the LHC. Okay, so as I said, this is the dominant production mechanism for the Higgs at the LHC, and it is called gluon fusion. Now, in gluon fusion, you produce the Higgs, but in principle, nothing else. So if you search for the Higgs, you just search for its decay products, but you don't care about anything else. This is what the experimentalists call an inclusive search. Inclusive means decay products, the rest I don't care. However, there are also associated production mechanisms in the standard model. The most important one is called vector boson fusion. So vector bosons have a coupling of something like 0.6 to the Higgs, so this is not small. So you can produce it from two valence quarks in the protons. You exchange between them your vector boson. This radiates a Higgs. Now, in this case, you have two quarks in the final states. And if quarks hadronize, their signature at the LHC is what is called a jet. So what you see here in your detector is the decay product of the Higgs plus two forward jets. Now, here you see you have three particles in the final state, and this is always suppressed by phase space. So phase space, like a loop, for each particle, you approximately lose a factor of 1 over 16 pi squared. So the experimental signature is clearer here, but it is less likely to have it because of this phase space suppression. Another process is what is called Higgs Strahlung. So from an off-shell W and C, you radiate a Higgs and you get an on-shell W and C. Now, this is very hard to see at the LHC because of the background and the small production cross-section, because of the off-shellness of W and C. But with the C and the quarks replaced by leptons, this is the dominant production mechanism at lepton colliders. So if you want to get something like ILC or FCCE, so future lepton colliders, then this process with a C here becomes very relevant. The last process, which is even harder to measure, is TT bar associated production of the Higgs. This is a very interesting final state, two top quarks and a Higgs. However, here you don't only have the phase-space suppression like you have it for vector boson fusion, you also have the suppression by the heavy top quark in the final state. So I think here at the LHC, we are not even at the discovery level yet. So this process has not been discovered. We have some small statistical indications, but we are not yet at the 5 sigma level here. Now, what you should keep in mind for later purposes is the main production mechanism of the standard model Higgs is gluon fusion. So this is why you can just do an inclusive search for the standard model Higgs. But for new physics, this must not be the case. Here, other production mechanisms might dominate, associated production mechanisms, and then in order to discover it, it might be better to do associated search. So looking for the decay hoders of the Higgs plus something else, then doing an inclusive search like you do for the standard model Higgs. Okay, So as I said, first you need to produce the Higgs. Here you see gluon fusion is by far the dominant channel. You see this is a log scale, so gluon fusion is dominant. One order of magnitude below, you get vector boson fusion. Another factor of 3 or so, you get Higgs-Strahlung, and then the smallest ones are BB bar associated production and TDH associated production. So this is why I said gluon fusion is dominant in the standard model, even if you take into account the experimental advantages of the associated production channels. Okay, now we have produced the Higgs. The next step is we must see its decay products, because this is how you infer its existence and its mass. So here, the dominant decay, no, not the dominant decay mode, the golden channel for finding the Higgs is the di-photon mode. Because photons are very clear, high energetic photons are a very clear signal at the LHC. So this is dominantly induced by W bosons. This is more important than the top loop, because for the Ws, you have 3 polarizations. So in fact, what you can see is that something like 80% of the diphoton rate comes from WW, and there's even a destructive interference with the top quark loop. Now, how this is done experimentally, so to see that there is really a Higgs, meaning a peak in your invariant mass distribution, is quite simple once you have done all of the very elaborate experimental analysis. So what I mean is, if the experimentalists did the hard job, they give you their data for the diphotons, even a theorist can do the analysis and see if there is a peak, meaning a new boson. So the way it works is you take the number of events as a function of the invariant diphoton mass, and then you fit to this smoothly dropping function. So this is your background-only hypothesis. One knows this function quite well, what works here, so you do a fit, you calculate a chi-squared, and you see how good your fit to data is. Then, in the next step, you add a resonance. You can take a Gaussian, a crystal ball function, doesn't matter too much. But the important thing now is you have to refit the background. So what you are now doing is you're doing a combined simultaneous fit to both signal and background, and you vary the position of your signal. And then what you find is you find in principle a chi-squared as a function of the invariant diphoton mass. And if you find a big drop in this chi-squared, then this means here you have a preference for a peak, and then this means here there should be a Higgs boson. And this is how it worked here at the very early times. I mean, here you see there is a clear peak, but this is not overwhelmingly big, but this is how you get it. And then you compare the chi-squared of your signal plus background hypothesis to the background only hypothesis. And if this is bigger by chi-squared of 25, you have your 5 sigma discovery. Okay, so this is why diphotons are so nice. You don't need much theory. Once you have the events, you just fit background and signal, and you see if there's a new Higgs boson or not. And the great thing about this resonance searches is you also know the mass. You don't only know that there's something new, you can directly see the mass from the position of the peak. Okay, now here are the decay rates of a standard model Higgs. Now, nowadays we know it's 125 GeV. But before the discovery, we didn't know, because the standard model does not predict the Higgs mass. It's a free parameter. So it could have been any other mass. So this is why people did calculate the things and made this plot. So here you see this is 2011. This is before the Higgs discovery, where we didn't know where it is. And now you see that the different decays are a function of the Higgs mass. Now, at 125, you see we are quite lucky. All of these decay modes can, in principle, be observed. However, if the Higgs would have been much heavier, it would have been different. So let's say it were 200 GeV, then in principle, you can only see the CC case or WW, but WW is difficult because you either have missing energy or you have hadronic final states which are difficult to see. But you would never see the diphoton rate because this just drops. So the branching ratio to photon drops dramatically after you open up the WW and CC channels. So once the Higgs mass is more than twice the W or twice the C mass, you can produce WW and CC on shell. So this decay width gets much bigger, and therefore the branching ratio, which is the partial width over the total width, gets much smaller. So if the Higgs mass were heavier, you would not be able to see the diphoton mode. So the diphoton mode is only a golden channel for electroweak scale Higgses, let's say between 70 and 160 GeV. Now, this might be interesting for people who remember the 750 GeV excess in diphotons. So this is always a criticism I have to hear about the electroweak scale Higgses, which I will tell you about later, is that there was the 750 GeV excess in diphotons didn't turn out to be confirmed. Now, what I always say here is the situation for what I will tell you later is quite different because we are talking about 95 and 152 GeV. So this is the mass range where you still expect a relevant partial width to photons, so a relevant branching ratio to photons. And we are in the middle of the spectrum. We are not extrapolating, we are interpolating. So these are two advantages because 750 GeV, I really expect the Higgs to decay to anything, but not to photons. So this is also why these models which were brought forward to explain the 750 GeV excess were so involved because it's very difficult to get a dominant rate to photons. In fact, for this, the Higgs should in principle not couple to anything in the standard model at tree level, but rather only to heavy new stuff in the loop. That's the only way you would get a dominant diphoton rate at such a high mass. So the takeaway message here is diphotons are the golden channels for Higgses, but only at electroweak scale, let's say between 70 and 160 GeV. Okay. Now, for the standard model Higgs, one has measured all these possible decays here, what one can do. And then one can see, oh, it in fact fulfills the prediction that the couplings are proportional to the mass. This is why all these measurements nicely lie on this dashed blue line. So to a good approximation, the Higgs boson wedge we find has the properties which are expected in the standard model. So does this mean there are no new Higgses? Not at all. I mean, it's easy to add new scalars. There's no symmetry or consistency principle which forbids it. And as long as the mixing of the new Higgses with the standard model Higgs is sufficiently small, you don't mess up the standard model Higgs signal strength measurements and you are fine. So why should we look for...
Sorry, let
Yeah,
me
thanks.
interrupt you just because you've asked me to interrupt you.
Yeah, I'm happy.
So in this plot, of course you have the particles that can be easily identified. Do you think we'll ever have the capacity of being able to say, oh, we can tell the coupling of the charms or maybe strange quarks?
I think for charm and strange quarks at high luminosity LHC, they are hoping to get, for at least for charm, they are hoping to get something like a measurement around a precision of 3 or so. So if the Yukawa coupling of the Higgs were something like 3 times the one in the standard model, they might be able to see the process. But otherwise, for charm, you really need FCCHH or FCCEE.
Oh, really? Okay.
Yeah, but anyway, I'm not too optimistic about these channels because if the other channels don't show deviations from the standard model, why should these channels
Why
show
should, yeah,
deviations?
yeah,
Yeah,
sure,
it's
sure.
just difficult to construct a model where you have deviations in the charm and
Yeah,
strange coupling, but the top and bottom coupling are perfectly fine. So this is
perfectly
quite
fine.
difficult. So this
I
is
agree.
why I wouldn't say measuring charm and it's not useless, but measuring charm and strange cover coupling
It's not a high
isn't a
priority.
golden. Yeah, at least it wouldn't be my priority. I mean, it can be different for experimentalists, but it's nothing I would put on my very priority list. I will come later to what I would recommend to experimentalists.
Super.
Okay,
Thank you.
yeah. Yeah, thanks a lot for the question. Okay, and now this is also a good break. Now, why should we expect physics beyond the standard model? We have found the Higgs. Its properties are quite fine with what we expect in the standard model. So the reason here, of course, is we know that the standard model cannot be the final theory. There is dark matter. We know this from cosmological observations. Neutrinos are not exactly massless. So there must be something more like a right-handed neutrino. And we exist. So there's matter-antimatter asymmetry because more matter than antimatter survived the evolution of the universe. And also this I cannot explain in the standard model. I need something new, in general, new CP violating interactions. So it's absolutely out of question. The standard model cannot be the final theory. It's just that we don't know what the theory superseding the standard model is, because there are many options how to get dark matter, how to get massive neutrinos, how to make the matter-antimatter asymmetry. So we need to look for experimental guidance. And here, as I said, I would like to promote the idea of new Higgses. So first of all, as I already said, the reason for new Higgses is there's no reason not having them. I mean, you can easily add them to your theory. There's no problems with anomaly cancellation like you have for fermions, or you don't need a new Higgs mechanism to get massive vector boson. So it's in principle quite easy. And in fact, in nearly all top-down approaches like supersymmetry, we have new scalars. Then what you can also see here is the Higgs sector is at the origin of, I would call, the internal problems of the standard model. So the hierarchy problem, why is the Planck scale so far above the electroweak scale? The flavor puzzle, why are the fermion masses so hierarchical? Without the Higgs, there are no Yukawa couplings, no fermion masses, so this question wouldn't exist. And is the vacuum, meaning is the scalar potential stable? Also this, without the Higgs, you wouldn't have it. Now, the good news is you can, at least in principle, address all these problems by extending the Higgs sector. And also the observational evidence for new physics I discussed, like dark matter, neutrino masses, matter-antimatter asymmetry, and inflation, can be accounted for by extending the Higgs sector. And now there's another thing, and this is what I want to talk about here, is anomalies. So indications for new Higgs bosons, which are not yet at the discovery level of 5 sigma. And here I want to focus on the di-photon excesses at 95 and 152 GeV. Now, important, remember, vector boson cannot decay to 2 photons. So it must be a scalar unless you want to go for something non-renormalizable like spin 2. So if you have an excess in diphotons, in principle, it must be a new scalar, a new neutral scalar. So this is what I would call a Higgs. But all what this slide should tell you is the Higgs sector is a very promising place to expect new physics. Now, we have discovered one Higgs boson at electroweak scale. So you might ask the question, how is it possible that other Higgs bosons are hiding around the same mass if we have found the standard model Higgs? And here the answer is, it was first of all non-trivial to find the standard model Higgs. It took 2 more generations of colliders than expected before, because first of all, it's difficult to produce the Higgs. As we said, it's only via quantum fluctuations. And also the diphoton decay rate, for example, is quite small. The branching ratio is all the order of 10 to the -3. So finding the standard model Higgs is not easy at all, because at the electroweak scale, you have large standard model backgrounds. And especially if you have non-resonant signatures, like a Higgs decay to Ws or to top quarks, where you have missing energies from the leptonic decays, or where the hadronic decays are poorly measurable because of the QCD background, they can quite easily hide. So what can help, in fact, at the electroweak scale are associated searches. So as I said before, you don't look only for the decay product of the Higgs, so you don't look only for two photons, but rather for two photons plus something else. And with this, you can reduce the accidental background. Now, to illustrate this a bit more, let's look at the 95 GeV Higgs. So there is nothing much one as a theorist can do here concerning the discovery potential. So here we mainly have the diphoton channels from Atlas and CMS. They nicely agree. And here what you see is the p-value. So the p-value is the probability that what you see is a statistical fluctuation. So the lower the p-value, the more likely it is that there is really a new particle. And then you see here the p-value here, you go down to something like 10 to the minus 3 for the diphoton channel. It's also supported by tau tau and WW, but here you always have missing energy. So this is why they are broad. So they can be supporting channels, but they don't pin you down the mass. But now what I wanted to say here is about the diphoton channel, which is quite surprising, is that the best fit at the moment is 20% of a standard model Higgs. And we are at 3.4 sigma. So this means if you had a Higgs with 20% of the standard model cross section, that's not little. At 95 GeV at the moment, it only gives you a 3.4 sigma global significance. So from this, you can see how difficult it is to find new Higgses at the electroweak scale just because the background is so high there. Okay, so as I said here, the global significance is around 3.4 sigma. We only have inclusive information, so we don't know anything about associated production here. This is a little bit unfortunate, and this is something I would definitely like to encourage all experimentalists to look for. Look for the associated production of this 95 GeV Higgs. So look for something like gamma gamma plus leptons, for example. This would be a great discovery channel.
Sorry. So for instance, now with the standard model Higgs, the gamma gamma channel by itself already gives you a 5 sigma discovery on its own, right? And other channels already have a competitive enough statistics, right? Like I don't know if with tau tau you can get to 5 sigma or with BB bar, but they already give you, a statistical signal. So what's the problem here? Why don't we have the statistics to be able to say, oh, with tau tau we have something, or with BB bar we have something?
So first of all, it's also because the background is exponentially increasing at low masses. So it's much harder to see it at 95 than at 152. And as you see also, tau tau is not a discovery channel. So what you look here at is if the two taus decay hadronically, you have two jets, but you have a huge standard model background because QCD is just jets. So what you need to look for is at least one of the taus decaying leptonically. Now, if you have a leptonic decay of a tau, you always have missing energy. And once you have missing energy, you cannot reconstruct a mass peak anymore. And if you don't have a mass peak, it's much harder to see it because it distributes your signals all over the invariant mass range. So you lose in principle statistics. You are looking for some step functions or things like this. So it's much harder to see. And the same for WW. You don't see a peak. So this makes it so hard. And then together with the increased background, it's very difficult to see something at 95. As I said, even though the best fit is at 20% of the standard model, we are only at 3.4 sigma.
I see. Thank you.
Okay, yeah, thanks a lot for the question. Okay, now I want to come for another indication for new Higgs bosons, which you might not have heard about, and this is the one at 152 GeV. Now here, we even don't have any dedicated search from ATLAS or CMS, because it's quite close to the standard model Higgs mass. However, what you can do is you can look at what are called the side bands of a standard model Higgs search. So as you have seen at the discovery plot for the Higgs, if you look at the diphoton mode, you need also the invariant mass away from the standard model Higgs mass, because you need to fit your smoothly dropping background function. So you need the diphoton invariant mass not only at the Higgs peak, but also above and below. And this is what makes it possible, or even for theorists, to look for such a new resonance, because we have this data from the LHC collaborations where they searched for the standard model Higgs. So the standard model Higgs here is this magenta peak. The background is the blue line, and the new physics 152 GeV Higgs is the green line. And everything together gives you the red one. Now, I will show you in a few minutes why it's 152 GeV and not another mass. So you have to buy this for some time. But what I like to mention is that you see here also in between the two peaks, the red line is not agreeing perfectly anymore with the blue line. And the reason for this is you don't have a theory prediction for the background. You need to do a simultaneous fit. So you need to refit the background with respect to the case where you have only the standard model Higgs resonance. Okay, now you have to look at these channels in more detail. So here we took these ATLAS references, which looked for the production of the standard model Higgs in association with other signatures. So gamma gamma plus X, where X can be a lepton, a tau, two leptons, Lb, and so on. Now, the important thing is this plus X is not from the decay of the Higgs. We assume that only the photons are from the decay of the Higgs. So this is why we are looking for a peak in the diphoton invariant mass spectrum. This plus X is just an additional signature which helps us to reduce the background, just because it's less likely to produce two photons and a lepton than to produce two photons by chance. Okay. Now, as I said, we have these channels here. So you see there is a peak in one lepton. There's a very nice peak in one tau. There is nothing in two leptons. There's a nice peak in Lb, and Lb here means at least one B-jet, at least one lepton. There is nothing in leptonic top decays, which means exactly one lepton, exactly one B-jet. There is a nice peak in four jets, a nice peak in missing energy greater than 100 GeV, but not much in missing energy greater than 200 GeV. So this asks the question, how can you produce a Higgs that decays to two photons together with one lepton, but not with two leptons, together with one tau, but not together with two taus, together with Lb, which is, as I said, at least one lepton, at least one B-jet, but not with exactly one lepton, exactly one B-jet, and moderate missing energy. Unless you have a model which can explain this pattern, you won't find a significant preference for new physics. And now this brought me to the idea of the Drell-Yan production of a charged Higgs and a neutral Higgs. Now, Drell-Yan production of the standard model Higgs doesn't exist at all, because this would be the charged Goldstone. And the charged Goldstone is part of the W boson. So in the standard model Higgs, this would be Higgs Strahlung, not Drell-Yan production. Now, as you see here is we want to produce a charged Higgs and a neutral Higgs from an off-shell W. So this means the new Higgses must be in a non-trivial representation of SU2, either doublet or triplet, because otherwise you have multiply charged Higgses, and this would be excluded at this mass range by multi-lepton search. So, as you see here, we produce the neutral Higgs, this decays to the two photons, and this comes together with the charged Higgs, and the charged Higgs usually decays into the particles which are heaviest but still allowed by phase space. So this would be tau nu, WC where one is off shell, or top with off shell top, top bottom with off shell top. Now let's take the tau nu channel, and then you see that it works quite nicely. So tau nu gives you, of course, one tau but not two taus. From the leptonic decay of the tau, you get one lepton but not two leptons. And from the neutrino, you get moderate missing energy. So this fits quite nicely. Also, top-bottom works because from the decay of the top, you get the lepton and the beachhead. So this gives you two beachheads and one lepton, but not exactly one beachhead and lepton. So this can explain why the signal is in LB, but not in TLAB. Okay, now let's try the new Higgs being an SU2 triplet with hypercharge 0. SU2 triplet with hypercharge 0 has just two components because it's a real field, a neutral component and a charge component. The neutral component can get a WEF. Triplets break custodial symmetry. This means this only gives a mass to the W, but not to the C. So you can test it from electroweak precision observables. There's still space for something like a WEF of a 1 or 2 GeV here, because there's a slight preference for a heavier than expected W. But what is also important is, as the neutral component only couples to W's, it also only decays to it. And because the WEF of the triplet must be small because of electroweak precision data, the charged and the neutral component must be quasi-degenerate because their mass splitting is proportional to their small WEF. And this makes the model extremely predictive. So you have a charged and a neutral Higgs. For LHC purposes, their masses are quite degenerate. You know the production cross-section as a function of the mass because you know the electroweak gauge coupling. And you know the branching ratios of the charged Higgs because they all are proportional to the WEF squared. So the partial WEFs are all proportional to the WEF squared. This means in the branching ratio, the WEF drops out. So also the branching ratios of the charged Higgs are only a function of the mass. So this means you know the production and you know the plus X as a function of the mass only. The only thing you don't know, because here several contributions enter, are the branching ratios of the neutral Higgs to two photons. So now what you can do is you can do a fit to the branching ratio as a function of the mass of the neutral Higgs. And then you see here one lepton, again, a small preference, nothing in two leptons, nice peak in one tau, nice peak in LB, nothing in TLAB, something in 4 jets, then the peak in missing energy. And if you combine everything with 1 degree of freedom, you see this very nice peak here. So the central value, the best fit, is something like a branching ratio of the neutral Higgs to two photons of 1%. And now you see 1 sigma, 2 sigma, 3 sigma, 4 sigma. So this is nearly exactly a preference of 4 sigma at 152 GeV. And you see all the other wobbles go nicely away, and only this nice peak is left. So this is the reason why at the beginning in this plots with the number of events, I showed you the only showed you the peak at 152 GeV, not at another mass. Okay, so I would say this is already quite nice. This is the highest significance for a narrow resonance ever observed at the LHC. The caveat is it's done by theorists. So the experimentalists haven't done a dedicated analysis here, but the good news is at least I was able to convince them that they will do this in the future. So they are taking it seriously enough to do a dedicated search for such a triplet. So for gamma gamma plus X in this low mass range.
Sorry,
Okay,
for this you used real data, right?
this is all real data. So
right.
what we used here is this data which Atlas provided in these two articles.
Atlas.
So
Okay.
all the data you see is from Atlas. We just digitized their values, or we got it from
Yeah.
HEP data. And then what we did is we reproduced their fit. So we reproduced the magenta standard model peak and the blue background. And then we added our signal. So we just said we test a different hypothesis, which was not done by Atlas and CMS. We test the hypothesis of two resonances in the spectrum.
Sure.
And then what we find is that there is a preference of 4 sigma for a second resonance in addition to the standard model Higgs at 152 GeV. Okay,
Perfect.
thanks a lot for the question. Now, as I said, here we have to wait for confirmation from the LHC experiments, but this doesn't prevent us from going further. So, as I said, we have a charged Higgs at 152 GeV, so also the neutral Higgs should be around this mass. Maybe 150, maybe 154, doesn't matter too much. But it must definitely be lighter than the top with 174 GeV. So the top quark can decay to the charged Higgs and a bottom quark, and the charged Higgs then decays to WC dominantly if it is part of a triplet. So this is really a signature that is predicted by our model. And now what you can see here is your final state is WWC plus 2 beachheads. And this is exactly the same as ttZ in the standard model. So in the standard model, top decays to WB. So two tops means WWBB. And then in addition, the C has exactly the same signature. So what we did is we looked into the standard model measurements of ttZ, and we investigated the option that there might be a new physics pollution from this process. And then what we find here is this yellow-green band. So this is the web of the triplet, which can be directly translated into a shift in the W mass. This is compatible with electroweak precision data. So electroweak precision data tells you everything below the blue line is allowed. So we find a 2 sigma preference for new physics around 152 GeV. It's compatible with electroweak precision data, and it's also compatible with the direct searches for the tau nu and tau strange channel done by Atlas and CMS. So if the LHC observed less events than expected in ttZ-like channels, our model would be excluded. But they observe a 2 sigma preference where even the shapes of the signals fit our model. So this is why, even though it's only 2 sigma, this you can count as supporting indirect evidence for a Higgs triplet. Now, we can try to be a little bit more speculative and look at differential top quark distribution. So if you go here, TT bar production and decay in the standard model is TT bar going to WWBB, the W decaying leptonically. And now to reduce background from photons and C, you take opposite sign different flavor leptons. So mu plus E minus or mu minus E plus. And then you can look at the angle between these two leptons or at the invariant mass of these leptons. Now you see there's nothing resonant here, so you don't expect a peak in the spectrum. But what you see is that there are more events than expected at low masses and low angles. So be careful here. Atlas is making it more complicated than necessary. They are showing Monte Carlo, meaning standard model over data, not data over standard model. So this means a dip is in excess. Okay, that's important to notice. So if you are below 1, you have more events than expected. And here, if you are above 1, you have less events than expected. Now, as you see here, we have too many events at low angles and too many events at low masses. Now, can this be due to new physics? And here the idea is a heavy Higgs decaying to two lighter Higgses. One going to WW, the other one going to BB bar. So this is the same final state as TT bar in the standard model, just with a different kinematics. And now you might see the connection to what we discussed so far. So which Higgs decays dominantly to WW, a triplet, and what Higgs decays dominantly to BB bar, something that is very light. So this could be 95 GeV, and this could be 152 GeV. So this is the hypothesis we tested. We plugged this into mud graphs. So a heavy Higgs around 270 GeV decaying to 152 and 95 GeV, going to WWBB. And then we simulated this and we looked at these differential distributions, and it turned out, in fact, that the shape works. So you get events at low masses and low angles. And the very nice thing is you also solve the deficit at high masses and high angles, because these are normalized distributions. So this is like a seesaw. Here you have too few events, here you have too many events, but if you put more events here, then also the other side goes up, and you can explain both the surplus of events and the deficit of events at the same time. And in fact, if you look at the significance, it's breathtaking. It's at least 5 sigma, even for the standard model simulation, which agrees best with data. Now, one caveat is here. This did not include toponium. Now, this is a hot topic. How much does toponium affect the differential TT bar distributions? So the general story is here for delta phi, not too much. For MLL, probably there is a relevant impact, but not enough to explain the whole difference. So this can still be new physics. And now what's the very nice thing is that there's a twofold agreement. So first of all, if you look at the mass of the Higgs going to WW, this is MS here, and you determine this from the TT bar differential distributions, you find something like 151 plus minus 6 GeV. So that's perfectly compatible with 152 GeV, which is from the di-photon measurement. So a completely different experimental measurement with very different final states points towards the same mass range as the di-photon excess. And if you assume that S is a triplet and S prime is a singlet, you know the cross-section here, the total cross-section to WWBB from differential TT bar distributions. And since you know the branching ratio of singlet to photons, you can predict the 95 GeV diphoton signal strength. So this is the red region again, here the Y extension of the red region. And this nicely agrees with the measured diphoton signal strength for the 95 GeV Higgs. So there is this twofold compatibility. The mass of the one going to WW is compatible with 152, and the signal strength for the one going to 95 is compatible with the diphoton measurement. So as I said, this is a bit more speculative, but it's definitely quite nice. Here, this is just to tell you we have a UV complete model, which can give you this asymmetric Higgs signature. And the nice thing is, this was already proposed more than a decade ago by Ramsey Musolf to give a two-step mechanism for electroweak baryogenesis. So there might, in fact, be a relation of this model with the big question about matter-antimatter asymmetry in the universe. And this already brings me to my conclusion. So I hope I was able to convince you that new Higgs bosons are very interesting research area. We have nice indications for Higgses at 152 and 95 GeV. The one at 152 has even 4 sigma. It could be a triplet. In this case, you should see something in ttZ. And in fact, you do. And if you want to be more speculative, maybe the two together, 95 and 152, could even provide a simultaneous explanations of these disagreement in the differential TT bar distributions observed by Atlas and CMS. So thank you very much for the attention, and I'm looking forward to questions.
Super. Thank you very much for the talk. Um, I have so many questions that we could be here until tomorrow. So
Oh,
let me
I have time, no problem. We can continue, don't worry.
yeah, but then everybody else will kill me. So let's start with with everybody else and see if they have any questions. Yeah, Carla, go
I
ahead.
have one is related with your conclusion. Very nice with for the talks. Was very clear for me. So what next? So you have these two hints, and now what? What do you need to continue to see what it is that?
Yeah, so of course I'm partially relying on the experimentalists. So they promised to do this dedicated searches for 152 GeV, and I hope they will also look for the associated production of 95 GeV. So if my model here is correct, what you predict is sorry, what you predict is here, so this is 95, this could also go to 2 photons, so you predict gamma gamma plus WW. So this is the smoking gun signature of this model. And there is even a search of gamma gamma plus WW by CMS, but unfortunately they stop at 100 GeV. They don't go down to 95 GeV. So I don't know if there's anything at 95 GeV. So the experimentalists should look at the associated production of 95. This would be very important. The other thing is, even if they don't do dedicated searches, if they do again this associated production of the standard model Higgs with run 3 data, we can again look at the sidebands and see if there's anything. And then, of course, there's also the study of all of these non-resonant signatures, TT bar, ttZ. Also here, we don't have a dedicated analysis. So this is again something that experimentalists, of course, could do much better than our naive recast of their analysis. And I hope they will also look at this into some point. What is a little bit problem, if I might say this here, is that experimentalists somehow got a bit disappointed with standard searches, and now they're investing a lot of manpower into exotic non-standard searches and such more standard channels, which are usual signatures of electroweak scale Higgses, didn't receive too much attention in the last years.
Okay, thank you.
Super. Any more questions? So first, you looked at ttZ production
Yes.
from the way that the H plus minus decayed. What about WWZ production? Is there anything there?
So there's no excess in CC to 4 leptons. And this is in some sense good for the triplet, because with zero mixing, the triplet only decays to WW and to CC.
Can you repeat that again, please, sir?
So the triplet
Yes.
only gives an effect in the W mass or contribution to the W mass, not to the C mass.
Yeah.
Therefore, in the limit of zero mixing with the standard model Higgs, the triplet only decays to WW and not to C bosons.
Oh,
So one should not see anything in Higgs to 4 leptons. And in fact, there is nothing in Higgs to 4 leptons.
okay.
So that's the good thing for the triplet. So you don't see Higgs to 4 leptons. So this also means you should not see CC plus W or something like this.
So what I was wondering from this plot, right? You have the charged Higgs going into WZ.
Yes, so that's what's the dominant decay mode in the triplet. Now, it will also go to tau nu, this is correct, but this is much harder to see.
No, but my question was, I mean, if this can also give a contribution to something like WWZ production. That was what I was.
Yeah, yes, in fact, but that's a different mechanism that's here. So if you look here, you have the Drell-Yan production of the charged and the neutral component, right? And now the neutral one can go to WW, and the charged one can go to WC. So if you lose one of them because it decays electronically, you are in fact getting WWC.
Okay.
And yes, so these are then multi-lepton searches, but you see here the cross-section is only around 400 femtobar. So this is not huge. And the nice thing is, in all of these channels, which the experimentalists call VVV, so CCW, WWW, CWW, all analysis see more events than expected, except one CMS analysis, they see less events than expected. So they are somehow making the picture inconclusive. So in the end, the triplet, but it's also not disfavored with respect to the standard model. We wrote an article on this recently, but if this one outlier analysis from CMS were not taken into account, there would in fact be a nice preference for this Higgs triplet in multi-lepton or multi-boson final states.
Okay.
Yeah, excellent question. Thanks a lot.
Okay. So we have time for one last urgent question. I don't know if there's anything. Yeah, Roberto, go ahead.
Yes.
Last
Hi.
urgent question.
Hi, Andreas. Very nice the talk. I was wondering, because when it's very interesting the part with the triplet Higgs. So is it compatible? Because I'm trying to figure out the numbers. In the case of assuming that this triplet is part of the type 3 CSO, in the sense that you
No,
have
that's
the
not working,
triplet
unfortunately.
giving mass to neutrinos
No,
also.
we need y equals 0 triplet. The one giving neutrino masses is the y equal 1 triplet. And the
Okay.
y equal 1 triplet has a doubly charged component. And you can't have a doubly charged component around 150 GeV because this would give a cascade decay and give you too many leptons. So this would in fact also show up in this in what you mentioned, CCW, WWC, and this would give too many events. So this is why a y equal 1 triplet can't be the 152, but you could have both in a Chorchai-Machalczyk-like model. So you could have y equal 1 and y equal 0. Y equal 0 is 152. Y equal 1 is a bit heavier, but the waves cancel so that you can restore at least approximately custodial symmetry.
Oh, okay. Thank you. Yeah, very interesting. Yeah.
Okay, so we're 10 minutes past the time, so I think we should stop here. So thanks again. Thanks very much, Andreas, for being here, for giving this wonderful talk. And to all of the viewers, we're off to our winter break. And we'll be all seeing you in August. The next talk is on the 19th of August. We're going to have Hanno Rain giving a talk. So please stay tuned and we'll see you all soon. Thank you all.
Thanks a lot. Bye-bye. Ciao.
Thank you.
Bye-bye.
Drop me an
Bye.
email if you have questions. Bye.
Okay, we are offline.
Okay, good. So
Very,
now I
very.
can relax. Yeah. Oh,